We're going to talk about how charges move, or what moves charges in semiconductor devices. There are two kinds of charge carriers, and we're going to talk about both of them and sort of where they come from and how they're same and how they're different. Again, a lot of this is highly theoretical, and it sort of lays groundwork for where we get to later. So a lot of what I'm going to talk about is just familiarizing you with the terms that kind of we use a lot in here. So, you all know that current is just the flow of charge carriers in a particular direction. Electrons move towards a positive voltage, and conventional current is in the opposite direction. Conventional current is in the opposite direction from electron flow because conventional current was described and used before they discovered that it was electrons that did it. So they had a 50-50 chance of getting the direction right, and they didn't. There are some places that even use electron flow for current. The military used to. I don't know if they still do or not, but it's just one of those weird things that conventional current actually does flow opposite to the direction of electrons. In semiconductors, electrons are the only things that move. However, the electrons in the valence band of energy move differently than the ones in the conduction band. Electrons in the conduction band are free to move and free to carry charge, just like a regular conductor would. Electrons in the valence band also move, but they can only move from atom to atom, which is a different type of movement. So therefore, the characteristics that describe those electrons are different. So at 0K, which is the coldest you can get, all the electrons are in the valence band, which is shown basically in this structure, and don't have energy to move. They're all just sitting there. There are 8 electrons around each silicon atom, and basically they don't do anything until the temperature starts to go up. And as the temperature goes up, electrons get energy. And different electrons get different amounts depending on where they are and what they're doing and how far away from the nucleus they are and all that. So they're not all in the same condition. They're not all under the same particular stresses, as it were, keeping them from moving or inviting them to move or whatever. But some electrons gain enough energy to move from the valence band to the conduction band. And when they do that, they leave behind a hole. So electrons go off. The electron that's up there at the upper right is considered to be more or less a free electron. It's in the conduction band of the particular structure, but it's free to move around. Electrons and holes in, and this is semiconductor material that's just a single crystal, intrinsic, pure semiconductor. They're always created in pairs, because anytime an electron leaves the valence band, it leaves a hole behind. So it creates an electron in the conduction band and a hole in the valence band at the same time. So when that happens, anytime an electron gets enough energy, it just basically leaves holes behind. And then you have sort of a bunch of holes in the valence band. The electrons have gone off to do something else. They are no longer involved with the actual structure. They're still floating around within the crystal, but they're not bound to any particular one atom. So the remaining electrons don't have enough energy to move to the conduction band, the ones that are around the silicon. But oftentimes they do have enough energy to move from an adjacent atom into that hole, because it's a very inviting thing to have an open spot And electrons will naturally gravitate towards those open spots because basically you've got some silicon atoms that are lacking an electron. And some electrons from other atoms will just move into those spaces to try to create some kind of movement. So you basically have electrons kind of moving around and holes moving and swapping places. And what we do is we consider the holes to be like positive charges that are moving. So even though it is really electrons that are moving, we consider the holes to be the charge carrier and the holes to move, which is kind of weird, but that's just the way it's done. And holes are considered to have the same charge as an electron because they really are like electrons. They're not real positive charges. They're more like lack of a negative charge in a way. But we basically consider them to be positive charge carriers in the valence band of any kind of semiconductor material. And if you apply some kind of voltage, the holes will actually move in the direction of conventional current. So that's one idea, is that holes actually move charge and holes are considered to be positive charges. Electrons are negative charges, holes are positive charges. Holes are in the valence band, electrons are in the conduction band. Electrons move freely. Holes are created basically from electrons moving from atom to atom, so it's a different kind of motion. Another thing I have to talk about, and this is kind of not unrelated, but it's like jumping to another topic because I have to cover all these topics, so when I talk about stuff, you'll know what I'm talking about. If we have electrons moving in a lattice, whether they're in the valence band or in the conduction band, they're going to be moving differently than they would in free space, obviously, because they've got a structure, they're moving around other electrons, they're moving around other atoms, so they're not moving like they would in free space. So there's forces acting on every one of these particles in the crystal. And we actually don't know what they all are. There's external forces, there's internal forces, there's all kinds of stuff going on, and we don't really know. But the total forces, obviously, are going to be the mass times the acceleration. We know that. However, since we can't figure out what the internal forces are, because there's no real good way to measure them, what we do is we actually change the mass of the particle to reflect what kind of forces they're experiencing. So rather than try to figure out what the internal and total forces are, we just use the external force and we say, well, it equals this mass that's changed a little bit times the acceleration, so that we could still have F equals ma and have it work. And this m star is known as the effective mass of a particle. And it takes into account what is going on internally inside the structure. So what this means is that electrons have one type of effective mass because they're moving in a certain way in the conduction band. Holes have a different effective mass. Even though they are also basically done by electrons, the electrons are moving differently because they're in the valence band. So what this means, if we have an electron in the conduction band, we say it has an effective mass of 1.808 times the rest mass of an electron. So it just seems a little bit heavier when it's in the conduction band. That's basically how you think of it. For a hole, the effective mass is actually just a little over half the rest mass of an electron, because it's a completely different motion and different forces that are acting on the electrons that are moving, that are causing the holes to move. So the effective mass is different. For every material, just 1 minute, the electrons and holes have different effective masses. So the effective mass of an electron might be greater in silicon, but it might be less in another type of material. Yes?
So in most ways, holes act as particles?
Yes. We consider them to be particles, even though they really aren't, and they're really just the absence of a particle. We consider them to be particles. That's one of the weird things about semiconductor devices. So when I talk about electrons, I'm only talking about the particles in the conduction band that are causing charge to flow. When I talk about holes, then I'm talking about lack of electrons that are moving in the valence band, and that's why it's different. So effective mass is basically a property of material, and every material has different effective mass that, there's like a table where you can look them up, so you don't have to guess or anything like that. It is also possible, it won't happen in here, but effective mass is something that's used not just in here, but in a lot of different places and a lot of different concepts. And it's possible to actually have forces acting to create a situation in which an item seems to have a negative effective mass. And that can happen. It's just mathematical. It's not real. But in here, we will not have any particles with negative effective mass. They will all just be tabulated and pretty easy to find. So now that I've talked about that, I'm going to go back to talking about something sort of super theoretical again. I know I keep going in and out of talking about super theoretical things and then things that are kind of practical like electrons and holes, but I need to talk about something else that is super theoretical again, just because we have to kind of understand momentum and how movement works inside crystals. So we can relate electron energy and momentum. We actually did that before when we were finding like the total energy. If we take rho squared over 2 times m, and the m is just the regular mass, not the effective mass, just regular mass. And that is also equal to the Planck's constant divided by 2 pi, that h bar thing squared, k squared, and k squared is what we talked about, k before. It's called the crystal momentum. It's also called the wave number. It's the k that we had in previous lectures. It just has more than one meaning. But basically, what it is, it's a momentum type parameter that describes motion inside a crystal versus motion in free space. That's all it is. You can just think of k as like a momentum. And the reason we have to talk about this is because of how momentum works inside actual crystals. So if you had an electron in free space, and if you were going to plot the momentum relative to energy, you would just get a parabola, basically, that as you got more and more momentum, you get more and more energy in both directions. So if you had momentum this way, you get more energy. If you had momentum this way, you get more energy. And if you had no momentum, you would have no energy. It's really simple. The motion in free space is easy because something moving in free space doesn't encounter anything to make it move or turn or any other forces, so it just basically is a simple parabolic relationship. In semiconductor material, the energy versus momentum plot is more complicated, but it does give us some clues as to what happens inside the material. So as electrons travel through the material, and these are generally either holes in the valence band or electrons in the conduction band, they encounter different potentials and different types of interactions they have with other types of atoms. So depending on the direction even that they're going through the crystal, it makes a difference in what they're encountering. So for instance, if you were to look at a face-centered cubic, and this is kind of looking at the side of it, and you're going in two different directions, you notice that in the 110 direction, an electron would actually encounter like 5 atoms, but in the 100 direction, it would only encounter 3, just depending on what direction it's going. And that can make a difference, and this is why K-space diagrams for semiconductor materials look different than the first one that I showed you. The diagrams, and this is not something I'm ever going to ask you to reproduce, it's just a simple diagram to help you understand something, hopefully. If we look at gallium arsenide and silicon, you can see that they have much different relationship between energy and momentum than just an electron in free space. Basically, for gallium arsenide, and this basically works with both, but you'll notice first the valence band energies are all negative. They're negative because the electrons in that particular area are bound to a nucleus, and negative energies are bound. And in order to be free and have positive energy, they have to move to the conduction band. They will all electrons will try to get as close to 0 as they can. So at the valence band, it looks like they kind of pop up to the top, or they float up there, because that's what they do. They kind of gather right in that area. But if they're off to a side or whatever, they gather differently. But they try to gather right at that area where the energy is 0. And then the conduction band looks really different, you'll notice, between the two of them. So first of all, the valence band looks the same for gallium arsenide and for silicon, and actually also for germanium. Germanium looks exactly the same. But you will notice for gallium arsenide on the left that the conduction band is kind of wavy, but its lowest part is directly above where the valence band point is at its closest point to 0. What this means is that an electron going from the valence band to the conduction band does not have to change direction. It can just go straight up. That means that it does not have to change its directional momentum, and that means that it requires less energy. This is something, we call this a direct bandgap semiconductor. This is one of those types of things I put on like conceptual questions. So gallium arsenide is a direct bandgap semiconductor. It means that electrons go from the valence band directly to the conduction band, and there's enough energy left over that you can actually have some cool stuff happen, which I'll say in a minute.
Sorry, what did you say it was called again?
Direct band gap. Yes. So with gallium arsenide, we have a direct band gap semiconductor, and when electrons go up to the conduction band or when they drop down, they actually use less energy to go from place to place, which means there's extra energy left over, which has a use later on. Silicon is an indirect band gap semiconductor, because in order for electrons to go into the valence band, they actually have to change direction. They have to go over in the 100 direction in order to get into the conduction band. Because of that, there isn't any extra energy left over when that happens. So why does that matter? Why does it make a difference if they're direct band gap or indirect band gap? Well, basically, this is what happens. If gallium arsenide, it always happens that I end up with slides that say what I just said. So there we go. The excess energy is released in gallium arsenide as a photon. So what do you think we use gallium arsenide for?
LEDs.
LEDs. It's one of those types of semiconductors that can be used for LEDs because they are a direct bandgap semiconductor and have extra energy when electrons go from the valence band to the conduction band or vice versa, and they release a photon. Silicon can't do that. Germanium can't do that. They do release something, but it's something actually called a phonon, which is not useful for anything. I'd actually never heard the word until I started teaching this class. And all compound semiconductors are not direct bandgap semiconductors. So gallium arsenide's a compound semiconductor, it's a direct bandgap semiconductor, but other compound semiconductors aren't. So just because it's a compound semiconductor doesn't necessarily mean that it has to be. Let's see. I said that, I said that, I said that, and I said that. That's probably good. The other semiconductor we use a lot in here is germanium, and it's also an indirect bandgap semiconductor, but it goes the other way. Instead of going in the 100 direction, it goes in the 111 direction to get to the end. So yeah, I jumped ahead and said all the things I was going to say before I got to the slide that said what I was going to say.